Okay, this video will be on inverse functions. This next lesson will be on inverse functions, but before we go through that, we will have to talk about a relation because all functions do fall under relations, but not all relations would be a function. So for the first part of this, what is the inverse of a relation? So here we're going to say that this is a relation that reverses another relation. So that's the whole idea of an inverse. And the notation for inverse relation is going to be r to the negative 1. Now this is not going to imply 1 over r. It's just going to be the notation for the inverse relation. Right? So looking at our examples, we're given a relation and we're asked to find the inverse of that relation. So we are going to swap our x and y values. That's really all it's asking for us to do. So for this, our relation, the first element is going to be negative 7, 0. The next one, 2, negative 1. Then we have negative 2, negative 4. And so forth, and the last one is going to be 3, 6. So again, we see that all we are doing here is changing places with x and y. That's important for us to remember. Okay, so now we also need to talk about one-to-one. And we're told by definition that a function is going to be one-to-one if the relation and its inverse are both functions. So again, that definition, we have a function for one-to-one has a, and you can abbreviate one-to-one relationship if the relation and make sure it's both of them and its inverse are functions. So that's important for us to realize when we're going through this, especially when we're asked whether or not a function is one-to-one. Okay, so we have a couple of tests that we can use. Notice the first test they remind us of is the vertical line test, and that's just used to tell whether or not our function or our graph is a function. Now the horizontal line test, that's checking to see, determine whether or not the inverse of a relation is a function. So here we're talking about the inverse when we do horizontal. And both the relation and its inverse must be a function in order for you to have a one-to-one function. So applying that horizontal line test, notice that for these first ones we're given several graphs and we need to know whether or not the relations are one-to-one functions. So notice for this first part, when we draw any kind of horizontal line, notice that we do end up with a function that is one-to-one. However, with this one, if we look at drawing those horizontal lines, this one we do not have a one-to-one relationship. Our next one, we would have a one-to-one relationship. Looking at 4 through 6, again, drawing those horizontal lines, notice, yes, we have a one-to-one relationship. And for this one, no, we're not, because the graph itself is a horizontal line. And then finally, for our next one, this one is not going to be, even though it passes horizontal, it does not pass the vertical line test. So this one would also be no. So the next part, we're going to transition from relations and inverse relations to talking about functions and the inverse functions. Now the notation for an inverse function is going to be f to the negative 1 of x. And again, that's not necessarily talking about 1 over x. Something else that we need to realize is that not all functions will have an inverse, and then they tell us some steps to go through to actually solve for an inverse, and we're going to look at that next. So starting with the first, we need to determine if f of x has an inverse, and if it does, then we're going to say yes, and then we're going to actually find that inverse. And then we need to state any restrictions to our domain. So let's go ahead and see if we can't find whether or not we have an inverse for this function. So starting out, we do need to change our f of x. We're going to change that back to y. That's going to be our first step. Our second step is we're going to exchange places with x and y. And then finally, we're going to solve this equation for y. So I'm going to add 8 to both sides. And then finally, I'm going to divide by 4. And notice you divide every part of the other side by 4. So we have this particular y is equal to x plus 8 all over 4. And we have to be careful here because this y is not really a y value. So we need to change this back into an inverse notation. And we're going to say f inverse is going to be x plus 8 all over 4. And now from that, notice that we can say we have a function, and then we don't have any domain restrictions here, so we don't have to state any. Again, it would just be, if we talked about the domain, it would be all real numbers, but this is saying just to state the restrictions. So we don't have any, so we don't have to discuss the domain there. All right, so moving on to our next one. Again, same process. We are going to go through and change f of x back to y. And then after we do that step, we're going to exchange places with x and y. So I'm going to have x equals 1/2 y cubed minus 1. Now we're going to solve for y, so I need to add 1 to both sides. Now, the next step, let's get rid of our fraction. So to do that, I'm going to multiply both sides by 2. And so whether or not you distribute that 2, it doesn't matter. You're welcome to leave it like it is. And then finally, the last step, we need to take the cube root of both sides. So I'm going to have the cube root of 2 times x plus 1. That's going to be equal to y, but again, we need to change our notation because that's not really a y value, it is the inverse value. So that f inverse is going to be the cube root of 2 times 2, or that is just an x plus 1, sorry folks. So it's going to be 2 times x plus 1. Now, as far as a domain restriction, we're not going to have any because we're talking about a cube root, not a square root. So here, our domain would be all real numbers again. All right, so moving on to this next problem. Now, this one, since we have a square, we might have some issues with this. Now, when we're talking about the inverse of this, let's go ahead and see what's going to happen. So we do have y equals, and I'm going to have x minus 4 all squared plus 6. And again, I'm going to change places with x and y. So I have x equals y minus 4 all squared plus 6. And again, we're going to solve for y. First thing I need to do is subtract 6 over. And so that's going to give me x minus 6 equals y minus 4 all squared. Now we're going to take the square root, and we're going to have something that's going to come up here when we do the square root. We need to incorporate plus or minus. And we have x minus 6 equals y minus 4. And then we would add 4 over. So I have plus or minus square root of x minus 6 plus 4. And this is going to be a problem because we're going to actually have one x value going to two different y values. So here that plus or minus is going to make this not a function. So here notice that we would really have no inverse for this, because we were going through and checking to see if we would actually have an inverse. And notice that, again, we could even look at the graph of this. And notice we would move right 4 up 6. But it's a parabola. And very quickly we see that if I do a horizontal line through that, this doesn't pass that horizontal line test. So we have no inverse. So that's something we need to watch out for sure. All right, moving on for our next problem. This one looks like it's probably going to have an inverse. If we remember, the parent function here is going to be something that looks like this. And so this would definitely pass the horizontal line test. So again, yeah, that's going to give us an inverse. So let's go ahead and find it. So we're going to say y equals 5 over x minus 8. We're going to exchange places with x and y again as usual. So we have x equals 5 over y minus 8. Now we're going to try to solve for our y. So the best way to do that is there's an old, call it Jedi mind trick, or an old algebra trick really. You can exchange places with this denominator and what it's equal to. So in other words, we have y minus 8 equals 5 over x. That is legal. And then we're going to add 8 over. So y equals 5 over x plus 8. And again, we know that's not really a y. It's f inverse. And that's going to be equal to 5 over x plus 8. All right, moving on with this. Again, here, if we wanted to investigate whether or not we're going to have an inverse, this is the square root function. It's been flipped upside down, moved back to down 7. And it looks something like this, so it will pass that horizontal line test. So let's go through and we're going to change f of x back to y. Then we are going to exchange places with x and y. Now we need to solve for y, so I'm going to add 7 over. And let's see, that negative, really, when we square both sides, that negative's not going to make a big difference. So we can square that. Now, if it had been any other number, go ahead and move it. But with the negative, it doesn't matter. We're going to square that. And we're going to leave it just like it is. X plus 7 all squared equals y plus 2. And then we're going to subtract 2 over minus 2 equals y. And so now we're ready to go ahead and do our inverse. So f inverse of x is going to be equal to x plus 7 all squared minus 2. All right. Now over here with number 12, notice the parent function here would be absolute value. We do have some stuff going on the outside, but just in general, this would have been moved left 1, flipped upside down with all kind of horizontal, vertical stuff going on. But more importantly, if we do our horizontal line test, it's not going to pass horizontal line test. So we can very quickly say no inverse here. Right? Here we have our cube root function going on. And do remember the parent function for cube root looks something like this. So this would pass the horizontal line test. So again, going back, we will change f of x to y. So we have y equals the cube root of x minus 9 all over 4. Exchange places with x and y. So we have x equals the cube root of y minus 9 all over 4. We're going to multiply this 4, bring it up here. So we have 4x equals the cube root of y minus 9. And now we're going to cube both sides to get rid of that cube root. So when we cube both sides, and you can either leave it like this. If you cube it, it's going to be 64x cubed. And that's going to give us y minus 9. And then we do need to add our 9 over. So we have 64x cubed plus 9 equals y. And finally, we know that this is not going to be the original y, that this was actually the inverse. All right, moving on. So for 3x squared, now they're restricting the domain. So let's think about what this is really telling us. We're only going to want one side of that parabola. So now it's almost like a piecewise function here. We're looking at the values greater than or equal to 0. And if we go ahead and plug in 0, we're going to be at -1 included. And that's a positive 3x squared. So notice that we're only looking at that one side of the parabola. So this would pass the horizontal line test because of this restricted domain. So that means we are able to go ahead and find the inverse. So we're going to start out again, y equals 3x squared minus 1. We are going to change places with x and y. We're going to add 1 over. Then we're going to divide by 3. And then when we take the square root, we're only going to look at one side of this. So we have x plus 1 over 3. And then with the square root, we normally put plus or minus. But notice we already know that we're just on the positive side. So we are going to leave this positive. We're going to negate the negative. But even inside this, we still have a domain issue. And that's going to come from our radical. So we do need to check our domain here. And we need to look at x plus 1 staying greater than or equal to 0. So notice that x has to stay greater than or equal to -1. So when we write our final answer, we do have our inverse function is the square root of x plus 1 all over 3. And then we're going to put a comma, and then we're going to state our domain restriction, which is going to be x is greater than or equal to -1. All right, so our next section is going to be talking about verifying inverses. So the first part, we need to talk about whether or not we have inverses. So two functions are inverses if they are reflections of each other over the line, or we could just say each other over y equals x. All right, so now we need to be able to verify these inverses. And so what we're going to do with this, we're actually going to find the inverse first, and then we're going to graph these two to see what all of this is really talking about here. So for the first thing, let's go ahead and verify our inverse. So we're going to have here y equals 3x minus 6. We're going to exchange places with x and y again. We're going to solve for y. And so this is going to be our inverse. Now, whenever we're graphing this, though, this looks kind of weird. So let's get this in that y equals mx plus b form. So when we divide this up, that's really going to be 1/3 x plus, and then 6/3 is 2. So now we're going to graph both of these lines. So the first line, let's go ahead and graph our original line. And I'm going to put that graph in a different color. Let's put that in red. So that first line that we have 3x minus 6. So minus 6, that's going to be our y-intercept. So we're going to move down to -6. And then we're going to count off our slope. And our slope is the coefficient of x, so it's going to be 3/1. So we're going to go up 3/1, up 3/1. And so we're going to connect those dots. And we're going to have this particular line here. So there's our first line. And again, that one was, let's see, f of x equals, I need to label my line. That was f of x equals 3x minus 6. Now let's go ahead and let's graph our inverse, which we had our inverse was 1/3 x plus 2. So we're going to go up to our y-intercept of 2, and 1/3 means that we're going to go up 1/3, and again up 1/3. Oh, that was just 2. Up 1/1, 2, 3. There we go. So now we have our other line doing something like this. Now we have to look and see, there's our line, and pretend that's a straight line. Now what we're going to do when we're verifying this graphically is now we're going to go ahead and we're going to put in the line y equals x, which is going to be just our general line through the origin all the way up, and notice that these are mirrored images of each other across that line y equals x. Alright, and that's what they want us to do graphically with this. Right, so let's look at our next problem, and we're still going to go through that same process. So here we're going to go ahead and swap our x and y. So we have x equals y cubed plus 4. We're going to subtract our 4 over and take the cube root. So we have the cube root of x minus 4. That's going to be our inverse function. And so this is where we're really going to need our parent functions to remember what they are going to look like. So for the first one, let's go ahead and we're going to graph that one in red. And so it's the cube root function that's been moved up 4. So we're going to go up 4. Plot our point, and then we know that our cube root function looks something like this. And then we're going, our cubic, now we're going to do our cube root function, and that one we're going to change colors. And notice that with that one, our cube root function has been moved to the right 4. So we're going to go over 4. And now we're going to sketch that cube root function, which looks something like this. And now we're going to try to reflect that over the line y equals x. And again, notice that it does have a mirrored reflection over y equals x. All right, now we're going to talk about how to verify the functions inverses algebraically. And so that's going to come in with our compositions while we looked at it. So we're going to have two functions. We're going to call them f and g. Our inverses if and only if, so that's why you're going to see IFF. That means if and only if. We have f composite g of x equals, and now we're going to reverse the order. So we're going to say g composite f of x, and both of those have to be equal to x. If that's the case, then they are inverses of each other. All right, so here to verify that we do have inverse functions, we are going to have to look at the composite in both directions. So for the first one, we're going to have to look at f of g of x, and then in turn we will go back and look at g of f of x. You have to look at both of them to verify. All right, so for the first one, f of g of x, so we're going to take our function g and substitute that into f of x. And so let's see what that's going to look like. We're going to change x to be 2x plus 7. Then we have minus 7, and all of that's over 2. And so when we collect our like terms, notice 7 minus 7. So we're going to be left with 2x over 2. And we can reduce those 2 since we're just multiplying. And so we're going to end up with just x. Now we go the other direction. We're going to take our function f and substitute it into the function g. So we're going to have 2 times x minus 7 all over 2, and then plus 7. Our 2's should cancel out, so I have x minus 7 plus 7, and so all of that, when we collect our like terms, we get x. So notice for both of those, we ended up with x on both places, so yes, these are inverses of each other. All right, so in 4, we're going to do the same thing. So for our first step, we need to find f of g of x. So here we're going to say f of g of x. That means I'm going to substitute the function g into f. So I'm going to have the square root of x plus 5 all squared, and then minus 5. And so that's going to give us x plus 5 minus 5, which is x. Now we're going to go the other direction. We're going to look at g of f of x. And so when we do that, I'm going to go and substitute in our x squared minus 5 in place of x and g. And then we have plus 5. And so that's going to leave me with the square root of x squared, which is just going to generate x for us. So again, notice these two did end up being x. So yes, these are inverses of each other. Okay, so again, we need to verify whether or not these are inverses of each other. So for the first, we're going to look at f of g of x. And so we're going to have some weirdness going on here. We're going to substitute in that whole g function. So we're going to have 3 over 2x minus 1 plus 3. And that's all over 2 times. And then we've got 3 over 2x minus 1. All right, so in our numerator, this would help if we got a common denominator, which we're going to put all of that over 1. And again, we're going to extend this, and we're going to find the product of the denominator, which is going to be 2x minus 1. Our numerator, we're going to cross multiply, so I'm going to have 3 plus, and then cross multiply the other direction. We need our distributive property. So that's going to be 6x minus 3. And so let's go ahead and collect those like terms. So that's going to leave me with 6x over 2x minus 1. And now let's look at the denominator. And here we're going to have 6, because this is over 1, multiply across the top and across the bottom. And so over here, we are going to extend this line as well. We're just going to bring this through. And notice here, now that we have this, we're going to do our keep, change, flip. And if we do that, notice we have 6x over 2x minus 1. And that's going to be times the reciprocal, which is going to be 2x minus 1 all over 6. And so notice the 6's will cancel. 2x minus 1's will cancel. So all of that cancels out, leaving an x. So let's go over and look at the other direction now. So we need to do, and I'm going to change color so these don't overlap. So now we need to do g of f at x. So now we're plugging f of x into g of x. So I'm going to have 3 over, and that's going to be 2 times, and we have x plus 3 over 2x, and then minus 1. So we have 3 over, and if we multiply it down here, those 2's will cancel. So I have x plus 3 over x minus 1. Again, we do need to find a common denominator here in the denominator. So we're going to have 3 over. This is going to be all over x. And so here we can do the product of our denominators. That's where the x comes from. Now we're going to cross multiply. So I'm going to have x plus 3 minus x. And so again, in the numerator, I still have 3. In the denominator, our x's are going to cancel each other out. So I'm going to have 3 over x. And again, if we keep going with this, it's the never-ending math problem. We're going to keep the top, change, and flip. And notice that the 3's do eventually cancel, so we're left with x. So here, these are inverses of each other. Now we're going to have more examples, and we're going to put all of this together. Notice that we need to verify these inverses both graphically and algebraically. So the first thing we need to do is actually to find the inverse here. So again, we're changing y, or f of x, back to y. And then we are going to exchange places with x and y. And we're going to solve for y. So we're going to have x minus 2 equals the cube root of y. We're going to cube both sides. Please don't multiply this stuff out. And we know that that y actually changes back to f inverse. Now, we found our original function is here, and our inverse function is here. And we're going to have to graph both of those. That's what it means to verify graphically what's going on with this. So let's go ahead and do the graphs of both. And this is where relying on those transformations and those parent functions is really going to come in handy. The first function we have is the cube root of x plus 2. So we remember that our cube root function is kind of laying on its side. It's been moved up 2. So our cube root function is going to look something like this. So it's going to go down. Okay, and then we've got our other function, which is going to be cubed. So we have a cubic function, and it is going to be moved to the right 2. And so this one is going to do something like this. And then we need to show that this is actually reflected over the line y equals x, so we do need to put in that line, y equals x. And there, we've shown this both algebraically, we've shown it graphically. Now let's go look at this algebraically. It just keeps getting better and better. So here, whenever we prove this, going to go through the algebra of it, then we're really looking at f composite f inverse of x. So we're substituting in what we found as the inverse into the original. So the original was the cube root of x, but in place of that cube root, I'm going to put the x minus 2 all cubed. And then we're going to have plus 2 out here to finish the problem. And notice that's going to give us x minus 2 plus 2, which is just x. Now we have to do f inverse of f at x. And again, same thing, we're just reversing our process. So we had x minus 2 all cubed, but in place of x, I need to put the cube root of x plus 2. And then we also had a minus 2 in there, all cubed. And so we're going to have the cube root of x, all cubed, which finally gives us x. So we have verified that both of those composites do equal x. Okay, we are first going to find our inverse, and they've given us a domain restriction, so that's good. That means we can find the inverse here with the squared. So again, we're changing places. We're going to make this y and then change places with those, so we have x equals y plus 4 all squared minus 2. We do need to bring over our 2. That's going to be y plus 4 all squared. We need to do the square root of both sides, and since we're staying greater than or equal to negative 4, it's going to be okay. We shouldn't have any kind of overlapping here. So we're going to have the square root of x plus 2 equals y plus 4. And then we're going to subtract over 4. So I have x plus 2 minus 4 equals our inverse. Now we're ready to verify this graphically. We're going to graph both of those. So the first one, I'm going to change up the colors a little bit so they don't get too messy. So for the first one, we do have a quadratic. And notice it only wants us to start graphing this when x is negative 4. So let's go ahead and substitute in negative 4. Notice we're going to get 0 minus 2. So we're going to start at 0, or negative 4, 0, isn't it? No, negative 4, negative 2, sorry. So we're going to go back 4 and then down 2. So there's our starting point with our parabola. And notice the parabola is turned upward. We can also do our transformation with this, which I think that's where we're at here. We can plug in some points. It's really not necessary. We can just go ahead. We know that this is a parabola, so we know what it's going to look like. And then we need to go ahead and sketch our inverse. Now with that inverse, we do need to look at the domain a little bit of that. And looking at this, the only way this is going to exist is if x stays greater than or equal to negative 2. So that's going to give us a good place to start. If we substitute in negative 2, then we're going to get 0 minus 4, which is going to be negative 4. So we're going to go back to negative 2, and we're going to go down to negative 4. And that's going to be our starting place for our other function. And keep in mind, this is a square root function. So this one is going to go something like this. And then we do need to go through and look at the line y equals x, just to show that this has been mirrored across that line. So there's our algebraic verification, or our graphic verification. Now for our algebraic verification, we need to first look at f of f inverse of x. So we're going to take our original, which was x plus 4 all squared, and inside of that, in place of x, we're going to put our square root of x plus 2 minus 4. And then we had plus 4 from the original, all squared, and then we have minus 2. So going through this, we are going to have the square root of x plus 2, all squared, minus 2. And then this one is going to end up being x plus 2 minus 2, which does verify us to get x. And now let's go the other direction. So we need to look at f inverse of f at x. And so that's going to be equal to, and again, we're going to substitute in. We had our square root. We had x, so in place of x, I'm going to have to put x plus 4. That's what we started with, x plus 4 all squared minus 2. And then we also had plus 2 under the radical. And then minus 4 out here to the side. And so under the radical, those 2's will cancel. So I have the square root of x plus 4 all squared. And then minus 4. And so we have x plus 4 minus 4. And that in turn is going to leave us with x. So we have verified our inverses algebraically.